Hey YouTube, welcome to Higher Math Solutions. This video tutorial is going to go over how to take derivatives of implicit functions. So implicit functions are functions that have x's and y's mixed together. So it's not a function of y in terms of x. It looks something where you have powers of y's and powers of x's all mixed together. This would be an implicit function. And to take derivatives of these, you have to use the chain rule. I want to start off with a simpler parabola type implicit function, y squared equals x. You could draw this simply by doing a parabola that is sideways. And you can see it's actually not a function at all, but it still has slope. So we would still be interested in learning what is the slope equations for this function. I'm going to go ahead and show you why you have to use the chain rule on implicit functions. So I'm going to go ahead and change y to f of x, which is just another name for y that you use as well in algebra. And I'm going to find the derivative of this function. To take the derivative of f of x squared, we need to use the chain rule. So I'm going to take the derivative of the outside first, but I will leave the inside the same. And then when I take the derivative of the inside, it is f prime of x. And then the derivative of x is just 1. And so this is what you need to be able to do on the implicit functions. Now I'm going to change everything back to the y, which is what we had it as. So instead of f of x here, I'm going to write a y. And instead of f prime of x, I'm going to write it as dy over dx, which is just another way of writing f prime. And this is the notation that we will use. But this right here comes from the chain rule. This is the derivative of the inside, which is the derivative of y, which is y prime. So let's do some examples using this method. Let's start off with this circle. A circle equation is x squared plus y squared equals to the radius squared. So we'll have the radius be 3. This is considered to be an implicit function because it's not a function of y in terms of x. So I'm going to start with my first term and I'm going to take the derivative. The derivative of x squared is 2x. The derivative of y squared, that is where you will apply the chain rule. So I'm going to take the derivative of the power, which will be the derivative of y squared is 2y, but then after I have to take the derivative of the inside as well, and the derivative of y is y prime, and I will write it as dy over dx. And then the derivative of 9 is 0. You're not done here. You want to solve for the derivative, so you need to subtract any terms over that do not have the derivative with it. So I'm going to bring the 2x over to this side. And then I'm going to divide by the 2y. And then this will reduce by 2's. And so the derivative of a circle is going to be negative x over y. Let's try a little bit harder one. This one right here is another implicit function because you see it's not a function of y in terms of x. It has y's mixed in with the x's. When I do this term, which is what I'm going to start off with, this will be a product, okay? So you have x times y squared. Your first function is x and your second function is y squared. So I'm going to take the derivative of the first times the second plus the first function times the derivative of the second function. Now since I'm taking a derivative of a y term, I'm going to do the power rule like normal, but then afterwards I have to multiply it to y prime because the derivative of the inside is y prime. And then this will complete the product rule for this first term. Again, don't put a y prime with this first term because you did not take the derivative of y squared here. You only took the derivative of the x. You do not put it until you actually take the derivative of the y term, which would be in the second term right here. Our next term is 3y squared. So again, you see that it is a y term. So again, I have to apply that chain rule implicit part. So I'm going to do the power rule like normal. So this will be the derivative of 3y squared will be 3 times 2 times y, and then 2 minus 1 would be 1, and then times y prime. Again, if it's a y term that you're taking the derivative of, you always will end up having to multiply it to y prime. And then equal to the derivative of 4x cubed. Since this is just an x term, you do not have to do anything special. You just do the power rule. So 4 times 3 is 12, and then 3 minus 1 is 2. That takes care of all the derivatives, but you haven't solved for dy over dx yet. So every term with the dy over dx in it will stay on one side, but everything else has to go onto another side. So this term right here needs to be moved over. So I'm going to get 2xy dy over dx plus 6y dy over dx equals to 12x squared minus y squared. And then once you get your terms separated, on this side, every term should have a dy over dx. You can factor out a dy over dx. And then once you have it factored out, you will divide what's left over to the other side. And this would be your derivative for this implicit function. Let's try another one. Let's do a trig function one. This will be sine of xy equals to 4x squared. So in this case, again, it is not explicit, it's an implicit function because you have x and y mixed together in the equation. So what I'm going to do here this is one term, to take the derivative of this, it's going to be a chain rule. So I'm going to take the derivative of the outside first, which is cosine, but I will leave the inside the same. But to take the derivative of the inside, that is a product rule. So I'm going to do the derivative of the first function first. The derivative of x is 1 times the second function, y, plus the first function times the derivative of the second function. Now again, since this is a y term, when I take the derivative of that term, I have to include that chain rule. So the derivative of y is 1, but then I would need to add that dy over dx with it. And this completes the product rule for xy. Then the derivative of 4x squared is just a normal power rule, which would be 8x. From here, I'm going to go ahead and take this cosine of xy and I'm going to distribute it through the parentheses, because again, I still want dy over dx to be solved for by itself. So this times this, do not multiply the y's together. I'm just going to put this y in front. So I will get y times cosine of xy, and then plus, again, I'm going to write this in the front, x dy over dx times the cosine of xy, and then equals to 8x. This right here is your only dy over dx term, so this is the only one that will stay on this side, but this term doesn't have it in there, so I need to subtract that over here. So I have x dy over dx cosine of xy equal to 8x minus y cosine of xy. And then for my last step, to solve for this, I'm going to divide the x and the cosine over to the other side. So dy over dx equals to 8x minus y cosine of xy divided by x cosine of xy. And this represents the derivative of our original implicit function. The cosines of xy's do not cancel out. This would be your simplified answer. There's one more example I would like to do. I would like to do a second derivative example, and I'm going to use the first one that we did, the circle, to help us out on this one. So for a second derivative, I want to find the second derivative using an implicit function. So I'm going to go back to the circle example that we did, and we ended up getting our first derivative as negative x over y, and we're going to use this one to find the second derivative. So you need to find the first derivative like we did, which is this one, and you want to make sure it's as simplified as it can be because you have to use it again, and you don't want to have any numbers in there that you don't need. So what I have to do though, to take this derivative again, I will have to use a quotient rule. So the quotient rule is the derivative of the numerator times the denominator minus my numerator times the derivative of the denominator. And since I'm taking the derivative of a y term, again remember, you need to include that dy over dx with the derivative part. And this is all over y squared. You're going to want to clean this up a little bit. Negative and negative makes a positive. And so this is a pretty cleaned up version for this one. Now what you need to do here though, anytime you see where dy over dx is, which is, in this case I have one place, you are going to have to replace it in the equation. So I'm going to end up with negative y plus x, and instead of dy over dx, I'm going to replace it with what our first derivative actually is. And then you will see that's what we have here. You're still not going to be complete though. What I want to do is I want to combine these two terms. To simplify it a little bit more. Now what I'm going to do from here is, we don't usually like seeing a fraction within a fraction. So I want to get rid of this denominator to make it look a little bit nicer. So to get rid of this denominator, I'm going to multiply every single term by y. So this times y will be negative y squared. This times y, the y's cancel, and I'm left with just x squared. And then y squared times y is y cubed. So you can see it looks a lot better than this form right here. Now on the second derivatives of implicit differentiation, there's one more thing you have to do at the end. You always want to look at your original equation, which was our circle, and you want to see if you can do anything of substitution into your second derivative answer. And actually I do see a similar equation from here to here. If I were to take out a negative, this is the exact same as what I started with. And what you're going to do is, I see that x squared plus y squared equals 9, so I will replace the y squared plus x squared with 9, and I will get negative 9 over y cubed. And so to take second derivatives of implicit differentiation, there's a lot of algebra involved, and then at the end you have to double check to see if there's anything you can substitute in at the end to make it look as simplified and as nice as possible. Thank you for watching Higher Math Solutions. See you next time.